Okay, this is Dr. Brown. In this video, we're going to talk about the extreme value of functions. In other words, we're going to use calculus to determine what the maximum value of a function is and what the minimum value of a function is. The first thing I want to mention is that if f is a function of x, which has a domain D, and of course the domain is the values of x that are you can calculate a value of f of x for. F has an absolute, or sometimes we call it global maximum value on this domain at a point C if all other values of f of x are less than or equal to f of c for all x in the domain. And the function is said to have an absolute or global minimum on the domain at c if all other values of f of x other than at c are more than or equal to f of c for all x in D. Just to show you an example, here are two functions that we're very familiar with. We are looking over a closed interval from minus pi over 2 to plus pi over 2, and we're looking at two functions. The first is sine of x, and the second one is cosine of x. And you recognize that the sine function has a maximum value of 1 at x equal pi over 2 and a minimum value of minus 1 at x equal minus pi over 2. Notice that these values happen to be on the endpoints of the interval. Now for the cosine function, you see that its maximum value is equal to 1.0 at x equals 0, and the minimum value occurs at 2 points, f of pi over 2 is equal to 0, and f of minus pi over 2 is equal to 0. So we're going to see that the min and maximum values of a function can occur internal to an interval, or interior we would call it, or it could be on the endpoints. Now here are 4 examples of a function that's principally y equal x squared on various domains. The first one is y equal x squared for x between infinity and minus infinity. And we see that this function continues to increase on the left and on the right, and there is no absolute max. It just continues to increase. However, at x equals 0, we have an absolute minimum. Now suppose we take essentially the same function but with a different domain, and let the domain be between 2 and 0, including the endpoints. That means you can put filled in dots at these endpoints because these points are on the graph. And so then we would say that the absolute maximum of the function is equal to 4 at x equal 2, and the absolute minimum of the function is equal to 0 at x equals 0. Now let's look at basically the same function except with a little bit different domain. Let's say that we have a heavy dot at x equal 2. In other words, the point 2 and 4 is on the graph, but we have a hole in the graph at x equals 0. So 0 and 0 is not on the graph. Now when we examine this, we would say that the absolute max is equal to 4. However, y never quite gets to 0. It approaches 0, but since 0 and 0 is not in the domain, there is no absolute minimum. It gets down as close as you want to. In fact, it gets down to 0.0001 or 0.00001 and as close as you would like, but it never gets to 0. The last example would be if the 0.00 were actually on the graph, but there was a hole in the graph at 2 and 4. And we say 2 and 4 is not on the graph. And so we would say there is no absolute maximum. The value of y gets as close as you want to 4. In fact, it gets down up to 3.9999, as many nines as you want, but it never gets to 4. So there's no absolute max. However, since the point 0 and 0 is on the graph, there is an absolute minimum. Now, this is a theorem that you will understand by way of a number of examples. It says that if f is a continuous on a closed interval between the points x equal a and x equal b, then f attains or realizes both an absolute maximum value of m and an absolute minimum value of lowercase m on the interval a to b. That is, there are numbers x1 and x2 between or on the interval a to b where f of x1 equals lowercase m and f of x2 equals capital M. So for all other for all other values of x, f of x is either more than or equal to lowercase m and less than or equal to uppercase M. Now let's look at several examples here. In the first function between a and b, the maximum occurs at this point x1, and the minimum, absolute minimum, occurs at this point x2, and that would be lowercase m. All other values of x are either less than or equal or more than or equal to capital M and lowercase m respectively. Now, in the second example, notice that at the endpoint A, the function has its absolute max, and at the other endpoint B, it has the absolute min. So here, the function obtains the absolute max at the left endpoint and absolute min at the right endpoint. And in the first example, this is an absolute max at an interior point, an absolute min at another interior point. And so this would be x1 and this would be x2. In the third example, we can clearly see that at say x2 we get an absolute maximum at an interior point and an absolute minimum at the left endpoint. And in the last example, you can clearly see that at this point x1 we have an absolute minimum, that would be lowercase m, and at the right endpoint, this case b is equal to x2, it has an absolute max. The whole point of this is that the extreme values of a function can occur at the endpoints if you're talking about a function defined on an interval from A to B, or they can occur at interior points. So one of the things you need to remember is when you're looking for the maximum and minimum, you need to look at interior points, and we're going to talk about where you need to look for interior points, and you also need to look at the endpoints. Now, here is an example of how we're going to classify or the classification of min and max. First of all, at this point, this is an absolute max. Looking between x equal a and x equal b. The next thing you see is m is an absolute minimum, but we have some other interesting points on this graph. This graph does have a relative peak here at this point, and this is called a relative max. Down here in this valley, we have a relative min. And on the right endpoint, we also have a relative min, which simply means that in the vicinity of b, of x equal b, all other points around it have a value that's greater. Now here's a very important theorem called the first derivative theorem. it says that if f has a local maximum or minimum value at an interior point C of its domain, and if f prime is defined at C, in other words, if it has a derivative at C, then that derivative has to be equal to 0. Here's a simple example of a function that has a relative max, and in this case also an absolute max. And you can see at this point C, L prime of C, the slope of the tangent line is 0. And you will see over the course of studying this subchapter that if we have a function that maybe is a little more interesting than this particular one, it could look like this. And if you look at this, you can see where you have the first derivative or slope of the tangent line equal to 0. And you can see that this would be a relative max, relative min, relative max, although not as large as the other mountain peaks you see here. Here's a relative min, relative min, and a relative max. And at all of these points, the first derivative is 0. Now, I want to show you these two examples to show you that if the first derivative of a function is 0 at a point, it's not necessarily a relative min or max. And these are just two examples that illustrate that. Here, y prime is equal to 3x squared. And it's equal to 0 at x equals 0. And you can see that at x equals 0, it is not a relative max or min. For the second example, we see that y prime is equal to 1/3 x to the minus 2/3 is equal to 1/3 x to the 2/3. And the first derivative is never 0. In fact, it's not defined at x equals 0. In fact, the tangent line has an infinite slope. And now we're going to have a definition that's going to help us find the absolute max and absolute min of a function. The definition is that an interior point of the domain of a function f, where f prime is 0, or undefined is a critical point of f. In fact, in the previous example, you saw that x equals 0 was a critical point where the derivative was 0, and the second one, 0 was a critical point where the derivative was undefined. Now here is the procedure we're going to use to find the absolute max or min of a continuous function of f on a finite closed interval. In other words, f is defined on an interval between a and b. You want to evaluate the function f at all critical points and all endpoints. So I'm going to mention to you is don't forget the endpoints. So look at all the critical points. Critical points is where the derivative is 0 or not defined, and looking at the endpoints, evaluate the functional value at these points, and then take the largest and smallest of these values would be your absolute max and absolute min. Now here we're going to have an example. In fact, we're going to have two examples. We have a function y equals 6 plus 4x minus x squared, and we are looking at it over the interval between 5 and 0. In this particular point, you can already see what the absolute min and max are, but pretend you had not looked at the graph and you just had the function. And here is what you would do. You would set the derivative, which is 4 minus 2x equal to 0, and we get 2x equal 4 and x equal 2 is where the derivative is 0. And so we now evaluate f at 2 is equal to 6 plus 4 times 2 minus 2 squared equals 10. So this is an interior point. And then we need to look at the left endpoint, which is x equals 0. F at 0 obviously is 6. And then we're going to look at the right endpoint, which is x equal 5. So f of 5 is equal to 6 plus 4 times 5 minus 5 squared turns out to be equal to 1. So now we look at all of these values, and the largest is f at 2. So we now have identified that f of 2 is equal to 10 is absolute max of this function, and the absolute min is 1 at the point 5 and 1 is the absolute minimum. So here the absolute minimum occurred at the right endpoint, and the absolute max occurred at the interior point where 2 was a critical value and the derivative was 0. The last example we're going to look at is to find the absolute maximum min of y equal x to the 2/3 power on the interval -2 to +3. We're going to do this first without looking at the graph. If we take the first derivative of this function, it's simply using the power rule, 2/3 x to the 2/3 minus 3/3, which is minus 1/3, is equal to 2 over 3 x to the 1/3, which is 2 over 3 times the cube root of x. Now, this is never 0, so the derivative is never 0. So the derivative is undefined at x equals 0. This is a critical point. Now we need to look at the endpoints. At the left endpoint, the value of the function f of at -2 is equal to -2 to the 2/3 power, which is equal to 4 to the 1/3 power, which is a cube root of 4. And at the right endpoint, f of 3 is equal to 3 to the 2/3 power, is equal to 9 to the 1/3 power, which is the cube root of 9. Now obviously the right endpoint looks like that's going to be the max. If we look at the critical value, alpha at 0 is equal to 0 to the 2/3 equals 0. So this is the absolute minimum value that occurred at the critical point where the derivative was not defined. And if you look on the next slide, we see the graph of the function. We see this sharp point at x equals 0, y prime not defined, and at the right endpoint at x equals 3, we see the absolute max, which is the cube root of 9, and at the left endpoint we see a value of the cube root of 4, which is obviously just in between. So here's the absolute min and the absolute max, and we will be working other problems like this in class on Monday.